Okay, finally, let's wrap up the work for this semester with section 5.4. Here in 5.4, we're going to concentrate on solving exponential and logarithmic equations. So we're going to go back to a couple of properties that we saw earlier with exponential functions and log functions called the one-to-one properties. Let's recall those. So with an exponential function, recalling the one-to-one property, it said if you had a to the x equal a to the y, then because those two bases matched, that is similar to solving x equal y. So a to the x is equal to a to the y if and only if the two exponents are equal. So it's like just sort of canceling out those two bases. Okay, then we had a one-to-one property for logarithms. That said, if you had log base a of x equal log base a of y, remember those two logarithms are matching, then x must be equal to y. So these are the simple exponential and logarithm equations we can solve using this one-to-one property. So let's take a look back at some exponential equations. When you have an exponential equation to solve, always check to see if you can use this one-to-one property. So basically what you're looking for is the base on the left to be equal to the base on the right. And when that's the case, you just set x equal y and solve that result. Take a look at this first example. I've got a base of e to a power equal to a base e of a power. Well, this satisfies the one-to-one property. The two bases are equal, so I'll just wipe those out, and it says that the exponents must be equal to each other. So x squared minus 3 must be equal to x minus 2. Now we see that ugly quadratic come into play. So how do I solve a quadratic? I get all the terms on one side. So I have x squared minus x minus 3 plus 2. All I did was take the x over to the left and the 2 over to the left to give me x squared minus x minus 1. There's my quadratic. Now let's work on solving it. Unfortunately, this quadratic does not factor. So we're going to need to use the quadratic formula. So let's work on setting that up. The coefficient of a is equal to 1, b is equal to -1, and c is equal to -1. I'm going to actually pause this, use the quadratic formula, and find your answers, and then come back and check. Using the quadratic formula, we get two answers, x equal to 1 plus the square root of 5 over 2, and x equal to 1 minus the square root of 5 over 2. So those would be our two solutions for that exponential equation using the one-to-one property. Notice this equation on the right. I don't have a base a equal to a base a on the right. The two bases don't match. However, I'm realizing that I can rewrite (81) as 3 to a power. If I can do that, then my bases will match, and I just have to solve for the exponents. So 3 to what power is equal to 81? 3 times 3 is 9, times 3 is 27, times 3 is 81. So actually it's 3 to the 4th power. So 3 to the 2x minus 5 equal 3 to the 4th. My bases are matching. Hooray, because that makes this easy to solve. All I have to do is wipe those bases out and solve for the variables. The exponents. Set the exponents equal to each other. Well, this is a pretty simple equation to solve. Bring the 5 over, so I'll have 4 plus 5, which is 9. And for 2x equal 9, I get x equal 9/2. There's my solution. When I can't use this one-to-one property, then I have a different format that I need to follow. So always look to see if your bases match, or if you can make your bases match, because that is always the easiest type of exponential equation to solve. If the bases don't match, then here is what we need to do. So I can't make the bases match. Here's 3 situations. Let's look at this procedure. We first have to get the exponent term isolated by itself. And what I mean by the exponent term, it's the base that has the exponent on it. Like 6 to the x is the exponent term, and he needs to stand alone. And he does in this problem. In the next problem, the term with the exponent is the e to the 2x. He needs to stand alone. And unfortunately, he doesn't here, so we'll have to do something. Let's look at the next one. The exponent term is the 10 to the 5x. Does he stand alone? Nope, neither of these 2 exponent terms stand alone, so we're going to have to get them by themselves. We're going to have to isolate them. Okay, so once I get the exponent terms isolated, then I'm just going to take the log of both sides. And you're going to see how helpful that's going to be, because the log is the inverse of the exponential, and one undoes the other. Okay, so isolate the exponent term, take the log of both sides, and then solve for x. So let's take a look at our first one. 6 to the x equals 17. The exponent term is isolated, so what I'm going to do is just take the log of both sides. I'm going to take an ln of the left and an ln of the right. You could use log if you wanted, but ln's just easier to write. How does that help me solve for x? Because I'm trying to get x by itself. Well, remember that property in section 5.3. If you have an exponent inside your logarithm, you can drop it in front of the log. And since the exponent is the part that has the x, that's going to be very helpful. So if I drop that x in front of that logarithm, I'm left with x times ln 6 equal ln 17. And how do I get rid of the ln 6 since it's multiplied by the x? Well, we're just going to divide both sides by ln 6. That's going to give me an exact answer for x to be ln 17 over ln 6. That's called my exact answer. If they wanted a decimal approximation, then I would go to my calculator and divide that out. ln 6 divided by ln 17. Let me make sure that's what it was. Backwards. Let's go ln 17 divided by ln 6. So the decimal approximation would be 1.581. So be careful. If they ask for the exact answer, we give them the answer in terms of logs. If they're asked for a decimal approximation, we go ahead and find that value. Now, how can I get this logarithm here, 8 times e to the 2x? How can I get that exponential. How can I get that e to the 2x to stand by himself? Well, since it's 8 times that, I can divide both sides by 8. That gives me e to the 2x equal to 3. Before we solve it, let's look at the next one. How can I get a 10 to the 5x by itself if attached to it is a plus 2? Well, I can subtract 2 and get 10 to the 5x equal to 7. So now here we are where we've isolated the exponent term, finished these two up by taking the log of both sides and then solving for x. Pause it, solve it, come back and check your work. Okay, so let's look at the solution to these two exponential equations. Remember the one in the middle, we divided by 8 to get the exponent term by itself. Then I said we can take the log of both sides, and notice how taking the ln of both sides is very helpful because this base is an e, the 2x, and the base on the ln is e. So I end up, when I drop the 2x in front, I end up with an ln e, which is just 1. Remember when the bases match, they cancel out, and you're just left with 2x. So 2x equal ln 3 solves as x equal ln 3 over 2. That would be your exact value. The approximation from your calculator would be 0.549. For this problem, we got the 10 to the 5x by itself by subtracting 2. So we got 7 on the right. And instead of taking the ln of both sides, I chose to take the log because the log is base 10. And when those two bases match up, they kind of cancel out and just give me 5x because log base 10 of 10 is just 1. Well, to solve for x, I'll divide both sides by 5 to give me a solution of x equal log base 7 divided by 5. That would be your exact value, but if you put it in your calculator, the approximation would be 0.169. I'll stop this video here and pick up with logarithm equations on the next one.